Hello guys, in this video we are going to cover isotopes. As a quick recap from our previous lessons, we already learned about neutral atoms where we have protons and electrons being equal in amount. We have also already covered ions, whereas whenever we have a charge that results from having an electron either gained or lost, and not just one, really just any amount of them, and that results in an unequal amount of electrons and protons. So we end up with a charge. In this video, like I said, we are covering isotopes. So we are mostly going to be focusing on neutrons this time around. And here on screen, what we have, the blue is what we've already covered. And right here at the very bottom, the last bullet point states that to change the mass of an atom, we have to change neutrons. And again, we can't change protons. That would result in changing the element itself. So what is an isotope and what are some of their properties? Well, isotopes are just atoms that have a different number of neutrons from the ones that we regularly see and can calculate for on the periodic table. So again, the only thing that is different is the number of neutrons. And because they have a different number of neutrons, that is going to affect the mass. Because remember, protons and neutrons are the ones that account for how heavy is going to be an atom. However, some of the properties are actually very interesting. They are identical in chemical reactions. So no matter if you're talking about two different isotopes of the same atom, meaning an atom that has the same atom, so it has the same number of protons, but it has different neutrons, it would still regardless behave the same way chemically. Now, if you think about it, it's not that whenever we talk about, let's say, carbon, we only talk about one type of carbon. Yeah, we're talking about atoms that have a total of 6 protons because carbon has 6 protons, correct? However, not every single atom of carbon is going to be identical. Some of them may have more neutrons than others, and that is going to result in having isotopes, right? So whenever we look at natural samples of an element, we are often looking at a mixture of the isotopes. So these isotopes are really just different versions of the same atom, if you would like to think about it that way. So here on screen, we have two examples, two versions of carbon. At the bottom, we can see that it has 6, so that represents the atomic number, meaning 6 protons. And at the top, the carbon on the left has 12, the carbon on the right has 13. And because of that, we can tell here that these are isotopes of carbon. They do not have the same mass. And remember, the difference because of that is because they just simply have a different amount of neutrons. The atomic number is the same. So protons are the same, amount of neutrons is different. And therefore, we can assume that these are two isotopes. Now here, we have carbon, but now we have 3 different versions. Here at the bottom, we have the atomic mass of each of them, 12 atomic mass units, 13 AMU, and 14 AMU. Again, how do I know these are all the same atom? Well, if we look at the top, we can see that they all have 6 protons. And based on the periodic table, we know that this is carbon. We also know that these are not ions, because if they were, they would have a different number of protons as they do electrons. And as you guys can see, each of them has the same amount of protons as it does electrons, right? So these are not ions. But could they be? Yeah, for sure, if there was a different number of electrons. Now here, the only difference that we have is the amount of neutrons, 6, 7, and 8 respectively. And that is really what accounts for the difference in the mass that we can observe here at the bottom. So how can we, aside from getting visuals like the ones we just saw and little tables that tells us how many protons, electrons, and neutrons there are present, how else can we tell that an atom is an isotope? Well, we already learned that just a regular neutral atom, we just write its symbol as it shows on the periodic table. And we know that if we have a charge, meaning different number of electrons and protons, we would have a plus or minus with the respective sign there. So that is usually what we associate with ions. Now, when we talk about having isotopes, Well, we can always write the atomic number just so that we can designate how many protons it has and the number on the periodic table. But more importantly, because we are talking about isotopes and we already established that isotopes have a different number of neutrons and that affects the mass, the way you would write that is right here with the mass number. Now, what mass number? Not the one from the periodic table, but instead the one that is established by adding the protons and the neutrons of that particular isotope, okay? So let's kind of do a comparison because this has been a lot of information that we've looked at for the last couple of videos. So when we have a neutral atom, same number of protons and electrons, we just have either the name or the symbol as it shows in the periodic table. When we have an ion, our atom has gained or lost electrons. So how would we write that? Well, we would just write its name as normal, or we could have the symbol, right, with the charge that designates how many electrons were gained or lost. And here, lastly, isotopes. Remember, atoms that have one or more less neutron than the average neutral atom that we see on the periodic table. How would you write that? Well, this is a little bit different. If you write the name, the full name, you have to have a dash with the new mass. So if you compare the mass from that oxygen on the periodic table, you will know that it is not 18. So whenever this number does not match the periodic table, so no matching with the periodic table, that immediately should raise a flag, and that way you would know, oh, this is an isotope. It does not match to what's on the periodic table, right? So once we have that established, then you could even, if you wanted to, write the simplified version with just a symbol dash the new atomic mass of that particular isotope. Or you could also do the symbol, where in the bottom we have the protons, and at the top we have the atomic mass, the mass of this particular isotope. Now let's do a couple of practice problems. And right here, make sure that every time you have any kind of information where you have to compare protons, neutrons, and electrons, you always have a periodic table available. You are not expected to memorize the entire periodic table and be able to answer questions like this one. So let's start with the very first one. We have neon 24. That dash 24 tells me this is an isotope, so my number of neutrons is not going to be the one that I would normally get if I was just looking at the periodic table. We will learn later what those numbers on the periodic table actually mean and what they represent. But for right now, we need to always, if it's given to you on a problem, you have to use the mass that is given on screen, okay? So we have neon, number of protons. No matter if you have an ion or you have an isotope, the number of protons of any atom will be the exact same one as it shows on the periodic table, atomic number. So neon is number 10 on the periodic table, so therefore it's going to have 10 protons. Here, I am not told that there is a charge. I don't see a little plus or minus sign anywhere. So therefore, I can assume that this is going to be neutral, meaning protons and electrons will be the same. So 10. Here, normally, for us to calculate the amount of neutrons, we would simply look at the periodic table and then subtract from the atomic mass that number 10 because that's how many protons it has. We can't do that here. Why? Again, because you are given the mass of that isotope. So you must use the one that is given to you, okay? So you will not use the one that's on the periodic table, which would be 20, right? Here, you're going to use 24. So 24 minus 10 gives us 14. Done with that first one. Moving on to the one in the middle. We are given 13 protons, so we would look on the periodic table and find the element that has atomic number 13, and that would be aluminum. So Al, you could either write the full name with the dash and the mass, or you could just do the symbols. Now here, I am given the neutrons, and I'd have to compare. I need to figure out, is this an isotope? So we would say 13 plus 16 gives us a total of 29. So the mass of this particular atom is 29. If I compare it to the one on the periodic table, I would see that it does not match. So for sure, I need to write it right here on the top, signifying that this is an isotope. Here, what you could also do is if you wanted to just be like fully specific, you could write the 13 right here underneath for aluminum, but it is not necessary because the atomic number of aluminum is not going to change. Now here again, you are not given a charge. You're not told that this is an ion, so therefore you can assume that it is neutral. So you would have 13 protons and therefore 13 electrons. Very last example, we have sulfur, which is number 16 on the periodic table, so 16 protons. And for the exact same reason I've stated before, there is no charge, so we can assume that it is neutral, so therefore 16 electrons. Now, here again, it's giving you the number 30 for the mass. So just a quick glance at our periodic table, we can see that the mass of sulfur is a 32. Therefore, we know that since they don't match regardless, we're given the number 30 for the mass, we have to use that 30 and we have to ignore the 32 that's on the periodic table. So 30 minus 16 is going to give us 14. Okay, again, at this point for the sulfur, you could write the 16 at the very bottom, but again, you don't have to because sulfur will always have 16 protons since that is its atomic number. Now that we have done some guided practice, let's go ahead and do some independent practice. So at this time, you would please pause the video, try this one on your own on a separate sheet of paper, make sure you have your periodic table. And remember, if you are given the mass, you have to use that mass for the calculation of the neutrons. That signifies that that particular atom is an isotope. So hopefully you have now taken a moment to kind of look at the 4 additional examples for independent practice. Here on screen, you guys have the answer key. Make sure that you double check all of your numbers. Here on the left, I have written down for nickel the 2 different ways that you could have written down its name with its designation of isotope with the mass 60. You don't have to do one or the other. Either one would be acceptable, but we do want you to understand that it could be written either one of the 2 ways. In our next video, we are going to talk about where does the atomic mass on the periodic table come from, and I will give you a quick glance at that, and that has to do with the amount of isotopes it has and what is its abundance out in nature. I hope you guys enjoyed this video, and I will see you guys on the next.